In this video, we're going to talk about three different types of decision variables in linear programming. We're going to talk about continuous variables, integer variables, and binary decision variables. So continuous variables are usually the ones that can take on decimal values, and examples of that can be when we're talking about amount of something. Let's say the amount of water, the amount of food that you can produce, if we have weight, and if we are talking about time, the length, right, when they can take decimal values. So these are the values that can take on a dollar amount, right? So these are examples of continuous variables. Also, when we have, and the next category is integer. So let me talk about this one, and then I come back to the continuous real quick, because there is an exception to the integer examples that we can assume that they're continuous. Integer, those are going to take whole numbers. They can't take decimal numbers, right? And by whole number, I mean, they can be either 0, 1, 2, 3, and so on, right? Integer values, those are the ones that we actually, the countable numbers. Those are that take like numbers, again, whole numbers, 0, 1, 2, 3, all the way to infinity, if that is the case. But the difference between integer and continuous variable is that integer decision variables are countable, and it matters. Like there is a significant difference between 1 and 2, and you can't really take on, let's say, 1.5 number of airplanes, for example. So number of stuff that matters, right? Number of, let's say, buildings, planes, ships, and like major stuff that you can't really go on, let's say, 2 and 3. You can't really take on 2.5 or 2.2. They can't take on decimal values, right? Countable numbers. But sometimes, so when you have continuous variables, those are the simplest variable when it comes to solving it. Those are easy, especially if you have all your decision variables in a model to be continuous. It's super easy. You can use simplex method. And even if you have millions of constraints, millions of decision variables, it may take some time, but it's solvable. You can come up to the unique optimal solution if it exists. But when you have integer variables, it adds to the complexity of the solution. It adds to the time that it takes, and then you have to go with. You won't be able to use simplex method. There are much more complicated techniques that you have to use for when you have integer decision variables into your model. So definitely, whenever possible, you want to go with continuous variables. In many cases, like examples of this, you won't be able to approximate, you won't be able to assume that the integer decision variables is continuous, but sometimes it's possible. For example, even when you're dealing with a countable number of something, let's say number of shoes to be produced by a company, by a shoemaker. If this is your decision variable, even though it's countable, even though it's going to be by nature, it's going to be an integer variable. But if this is in the optimality, if this is supposed to get, let's say, 1 million, let's say 1,000,010, uh, let's say 1, 2, if this is the optimal value, if you end up that, so if this is the optimal value that you're looking for, that really doesn't matter if you get a little bit, like maybe 1 or 2 below this, or 1 or 2 below above this, right? Even if you get, let's say, 0.05, even so, if this is the optimal value that you're looking, but even if you get this after you solve it, after you assume that this is continuous and solve it, if you get this, you can easily round it down. You can easily round it and get the actual value. And again, it doesn't really kill if we get our optimal value, let's say 1 or 2 units above or below this value. As long as we're close to this, that's fine, because we have a large scale value. We have a huge number here that we're looking for. And doesn't really matter if we go up or down a little bit. So we can approximate. When you can approximate the number, it's always better to take it as a continuous variable. So drop the integer assumption, assume that it's continuous, solve the problem with the continuous assumption. So in those cases, we can still assume that those are continuous, right? There's another group. So there are 3 types of decision variables. So I have to bring it up a little bit, bring my page up a little bit. The third group is called binary decision variables. So those are actually a subgroup of the integer variables, but with a minor difference. The difference is that from a numerical perspective, the difference is that they can take on 0 or 1, only 0 or 1. Those are binary decision variables. They can take either 0 or 1. And we use those binary variables when we're dealing with decisions that deal with only 2 values. Example of that, when we have yes or no type of situation, right? Do you want to go to the school today or not? That's the decision that we have to make. And the answer to that is either yes or no. Are you going to produce a specific product? The answer to that is yes or no, right? We're not talking about the amount of production. We're talking about whether there's going to be a production or not. So we're talking about the existence of things, right? Yes or no. Are you gonna go to a specific program? Are you gonna take? Are you gonna follow a specific program? The answer to that is yes or no. Are you gonna be friend with a specific person? That's it, a yes or no type of thing. Are you gonna take a course this semester? A specific course this semester? Again, this is gonna be a yes or no type of question. Are you going to go to business major or science major, for example? The way we formulate it, we make a 2 decision. So you decide for the business major. Are you going to go to the business major? Yes or no? And then are you going to go to the science major? Yes or no? So this example can be modeled using 2 decision variables, 2 binary decision variables. So when you have yes or no type of situation, yes or no type of decision to make, we use it as a binary variable. Are you going to invite a specific person to your party? Yes or no. All right. Are you going to go to a person's party? Yes or no. And so these are the examples. These are very, very important. Like I said, the simplest case is continuous. And then probably binary is still better than integer. Integer is usually the most complicated as far as I know, but you don't really need to be involved in the technicality, because the examples that we are solving in this course, those are small scale problem. And so depending on the existence of different types of different types of decision variables into your model, there can be, you may have actually four types of linear optimization models. The first one is that if all the decision variables are continuous, that's actually a linear optimization model, which is not in this slide. A linear optimization model is where all the decision variables in your model are um, continuous, are of continuous type, right? But then in integer linear programming models, the ones that we're going to address in this chapter, is when you have at least one of your decision variables either integer or binary, right? When you have all the variables in your model uh, defined to be integer variables, the whole problem is called an all integer LP. All integer LP means that all the decision variables are integer. When you have at least one, basically you have a mix of both continuous and integer decision variable. That would be called a mixed integer linear programming. And usually these are the ones that are the hardest, mixed integer linear programming. Hardest in terms of the solving, in terms of the time that it takes to solve them. Again, these are usually the concerns for the large scale problems. We're not going to be concerned about those because we're going to use solver anyways, and it's going to take a few seconds at most for the cases that we solve in this course. And then the next one is binary integer. LP is where all the integer values, where all the decision variables take on actually either 0 or 1 when they're all of binary type. If you have one continuous and at least one continuous and at least one binary or integer, then it's going to be called mixed integer, right? In practice, in a lot of cases, again, it's going to be very time consuming to solve binary and mixed integer and all integer LPs. So the first step usually in the solving process in the practice is to relax the integer assumption and solve the problem and see if the result that you get makes sense. Sometimes the result that you get, and again, depending on the type of variable, you may want to be if you get a decimal number, if the result is too large, if the outcome of your decision variables, the optimal value of your decision variable is too large, you may be able to simply round it up or down and just go with it, right? So it's always good to solve a problem that is called actually LP relaxation, and it's simply the same formulation, the same model, uh, except that you don't really care about the integer requirement. You ignore that and you solve the problem, you solve the LP using the simplex method, and then just take a look at the values. Do they make sense? Can you find a better answer close to those values? So that's usually the first step in large scale problems. In practice, this is what they do. Again, we're not going to be really worried about this one. We're not going to do LP relaxation in this course because the scale of the problems that we do are small. So Excel solver is able to solve them in reasonable time.